It is 2 hours UTC, and it's time again for Astronomy Daily Live. So, hey everybody, what's up? What's up? How's everybody doing this fine day? Hope everybody's well. I've got the chat up and running here. I'm going to start up my smartphone so I can sort of monitor things. So, come on in, friends. Come on in. I usually give everybody a few minutes to pop on in. So, hey, hope everybody's doing well. I'm going to start my smartphone there. Hey there, Tom. Hey there, Tom. So, yeah, uh, so whenever I talk about that movie, I call it the K movie, just so I don't have to say that that long word. So, so hope you enjoyed that. Uh, it's it's the kind of thing, and I don't. For those who haven't seen it, I'm not going to talk about it much. Um, but um, uh, the first time I saw it, it was just absolutely stunning. I think the what I like about it, what I like about it is the cinematography and the sound, right? And of course, that's all there is. But it's absolutely stupendously done. You know, he plays with exposure times, and yeah, he they just a fabulous job on that. And Philip Glass, um, he he wrote. I mean, uh, it is it is some of the most insane sounding music. It's just, I mean, at times it's just maddening, right? It's just absolutely maddening. But that's precisely what it's supposed to um, do. That's exactly the emotion that they're trying to put across, and the music and the images just does that, you know. So yeah, so anyone who hasn't seen the K movie yet, take a look at it. It's on YouTube. Now, yesterday when I checked um, this playlist out on YouTube, there were there were uh, there was a playlist, right, that had 8 10-minute segments, and then a ninth segment that had like almost 6 minutes. Okay, and I went through every single one to make sure that they all worked, right? Well, today when I'm playing it, number three, the third segment has been blocked. Has been blocked. So it's like, ah, man. So we did lose 10 minutes there, which that that's a pretty interesting 10 minutes. It's sort of the transition between um, sort of nature and wilderness and urban existence. And I wish that we could have seen that section because um, there's some interesting events that take place there. But I will let you discover that on your own. I can watch the K movie about once a year or so. I That's about as much of that as I can take. But when I was previewing it yesterday, I was like, oh yeah, I would really like to see this. So it's like, you know, um, so let's see, Catherine 313 in the chat, Uncle Bill in the chat, um, our instro in the chat, Ata, hey. Hey, so so yeah, the K movie is an interesting one. As I said, it's up on YouTube, so check it out for yourself. I encourage wearing some good headphones, um, because the sound is just so much better th- that way. Yeah, so very very awesome. I've got the uh, I've got the hydrogen hydroxide again, HOH. Now, this K movie is actually the first of a trilogy that I don't know if they had that originally planned as a trilogy or if it just was because the first one was I think pretty successful. It's like, oh, let's let's make a couple more. Um, and I tried watching the second one. I think I got through it. Um, and the third one, I I don't remember exactly what it was, but so yeah, the second one was sort of like, okay. Um, the third one was like, no, this is just not any good anymore. So, and I don't remember exactly why. I would have to see them in order to accurately describe uh, why number two and number three, at least in my opinion, aren't worth seeing. I think it has a lot to do with the fact that it's sort of the same kind of thing. Um, the yeah, I think there's only so many. Well, and this isn't exactly true, but um, there's only so many times you can show, like traffic like that, right? There's just so many times, and then it's sort of like, let's move on, let's move on. So after seeing the K movie, it's like, well, that's um, about as much as I want. But yeah, so that was really really fun. I'm going to be doing that every Monday at 0 hours UTC. I'm thinking of changing it to the midnight movie, right? Because it's 0 hours UTC. So yeah, um, I'm, I think I've currently called that room the lettuce bin, but I think I might change it to midnight movie. So that Mondays at 0 hours UTC every single week, I will be showing something, and it's going to be, either sort of artsy fartsy like like that is, or it's going to be some kind of scientific thing, right? Uh, um, like an episode of the old Cosmos. I want to show some connections uh, shows. You guys remember those? The first one, um, um, he did he did a Connections 2 and a Connections 3, but again, it's sort of like the K movie. It's sort of like, all right, you're starting to grasp at things. It's like, how many stories of connections can you possibly do? Well, there's an unlimited number of them, but it's like, how many can you actually talk about? That first series was really really great because he sort of covered everything, and I don't remember how many episodes there were. I want to say maybe like 10, maybe more, 13, 15, don't remember exactly. But yeah, so I mean, I want to see those. Maybe. maybe some space movies of some sort. Um, you know, but yeah, yeah, I don't know. And maybe if I can figure out how to most easily upload some movies that I have here that I like, like THX 1138, which of course is another. Uh, I think Francis Ford Coppola had something to do with this, right? He produced it. Yeah, executive producer Francis Ford. Anyway, so yeah, this is a pretty interesting movie, and it's George Lucas, right? This is actually George Lucas for his like his graduation project in film school was this short movie that he called THX 1138, and I forget how long it is, maybe 20 minutes or so. It's actually on here too. So what he did is, he made that, right, and then he graduated, and uh, and and uh, and so then years later, I forget exactly how many, um, he actually did a full production. James Duvall uh, is sort of the main dude, is THX, and yeah, it's sort of a futuristic, sort of dystopian type of a thing. Pretty interesting though. Pretty interesting. All right, well, cool. I'm not going to talk about that though. Point taken, Arnstro, for sure, for sure. All right, well, cool. I thought that uh, today I would talk about a class of objects that has in the past couple hours for me all of a sudden gotten a little bit more interesting. Um, and this is a class of objects that are called the Trans-Neptunian objects. So just as the name implies, these are objects that are orbiting the sun, but they're further away than Neptune. Um, so let's I'm gonna share my screen here. TNOs. TNOs. Now, we have a spacecraft that just a few years ago, just a few years ago, um, made a close encounter with a trans-Neptunian object. In fact, it made a close encounter with six, right? Six, yeah, six in sort of the same place. Um, yeah, I think I'm not exactly sure if there's necessarily a difference between a TNO and a KBO, um, because I mean technically KBOs are TNOs. So yeah, yeah. I think that's technically not exactly the same, but one is a subset of another, I guess. Yeah. So anyway, we had a spacecraft called New Horizons that made a close encounter with with the current, at least the current king of the Trans-Neptunian objects, Pluto, and the Pluto system. Pluto has a number of moons, and in fact, some suggest that Pluto and its moon Charon um, is more like a double dwarf planet than a planet and a moon. I think the distinction is where the barycenter is. So the center of rotation, um, the center of gravity. If if the center of gravity is is okay, hold on a second. We have a kitty alert. Hold on. If and Dennis Hands. If you haven't checked out Dennis Hands on Periscope yet, I suggest that you do, especially if you're new to astronomy. He's a teacher. He taught astronomy for like 30 years. Um, uh, uh, as a career, and now he's teaching like part time as well. So his approach is almost completely different than mine. He's trying to teach you things. So he gives a lot of quizzes and those kinds of things. But check him out on Periscope. Anyway, Dennis Hands, he has a great sense of humor, and one of the things that he says uh, is that if um, the Earth can't possibly be flat, because if it was, all the cats would have knocked everything off of it already. So, and the reason why I bring that up, Dennis Hands, as in hand. Yeah, I think if you search on Periscope for Dennis, um, um, all one word, Dennis R. Hands, right? Hands. Um, you will find him. Yeah. So yeah, we have already flown by and done an encounter with a trans-Neptunian object, and as I said, quite a number of them. I think Pluto has Charon and then four other moons. I think it. Um, and yeah, I think getting back to the center of rotation, I don't remember exactly, but I want to say that the barycenter between Pluto and Charon is outside of Pluto. Um, it's not contained within um, Pluto, um, but I don't recall exactly. But yeah, it's really close to what could be called a double um, a double minor planet. So very cool. And then a few other moons. Now the cool thing is about New Horizons is that after the Pluto encounter, they were like, okay, we can do this. We can do this. So, is there anything else, right? Because um, New Horizons is nuclear powered, so it has. I mean, it probably pretty easily has 50 years, right? Easy, yeah. So I mean, full power, right? 50 years, I would say, and then maybe it starts to lose a little bit. So we're so you know so far. Let's see. I think it was launched in 2000 and I want to say 2006, and it reached Pluto in 2015. And but now, but now they figured out that since it's like okay, since this works and we sort of know what to do, is there any other thing out there that we can go by? And it turns out that there is, and I believe it's December 31st of this year, I think. So, 5 more months or so, 5 or 6 more months. Yeah, I think they just woke it up again. It was in hibernation for a couple of years, I think, or maybe a year or so. It took a while to download all of its data, and then I think they told it to go to sleep, I think. But I think it's woken up again. Um, and and uh, and so yeah, they're going to be encountering another Trans-Neptunian object, and who knows what they're going to see. I mean, nobody has a clue. It's so far away and so small. I think it's pretty small. What's the let me share my screen. We're going to be going in lots of different directions, but the the basic theme tonight is trans-Neptunian objects because I do have a nice story to tell um, about that. So New Horizons. Let's see. I guess we can do this. This will probably tell us what we wanna know. Let's see if we can find out. There it is. So it's a it's a trans-Neptunian object called 2014 MU69. 2014 MU69. They've named it themselves. I forget Ultima Thule, I think is what they're calling it. Ultima Thule. Hey there, Bob Dog. Nice to see you in the chat. Hope all is well up there in the in the cold white north. Cheers. Anyway, so they're going to be doing a flyby of this trans-Neptunian object, 2014 MU69, and there's the countdown clock. Okay, cool. Yeah, that's sort of what I thought. I thought that there were five sort of total, and um, Pluto. So yeah, yeah, correct. Okay, now your fun fact number two, Arenstro, I'm not sure about. I'm thinking that the Berry Center between those other ones, between Hydra, Nix, um, um, Cerberus, and Styx, Um, oh, Kerberos. Kerberos. Um, I'm thinking that the Berry Center there. Ooh, I don't know. I mean, they're pretty much further away too, right? So, yeah, I don't know. I'm thinking out loud, but yeah, maybe you're right. Maybe you're right. It's regardless, it's pretty crazy. Pretty crazy, pretty crazy. Um, so yeah, like uh, they're saying January 1st at 5:33 UTC. I guess that's the actual time of the flyby. So yeah, that'll be uh, my time locally. That'll be what 10:33 p.m. on the 31st of December of this year. So yeah, very very cool. Don't know what to expect there at all. The um, oh yeah, we were gonna. Is there a? I wanted to see if there was a size, if they had a guess, a guess on the size of this object they're going to fly by. Um, I don't think that's going to help. Yeah, that's not going to help. I'm not quite sure. Fun facts, mission management, science. Okay, so yeah, they're not getting into that kind of detail here. Let's see if we can find it another way. It's one more, I think. Up too far. Because I think what I can do is I can. So 2014 MU69. 2014 MU69. Come on, Slowpoke. So they say that it's 30 kilometers in diameter. So these things are pretty far out there, right? Um, the closest it comes to the sun is 42 astronomical units. That's 42 times the distance between the Earth and the sun. So, um, so that is a very, very, very uh, small object, and small objects mean that they are going to be extremely, extremely faint. Um, do they have? Yeah, look at that. Apparent magnitude 26.8. Yeah, that's really, really, really seriously faint. Um, yeah, it's amazing that you can see anything there at at all, right? Because that's incredibly faint. Um, but they're going to fly by this thing at the end of the year. Yeah, they were able to uh, observe this object occult a star, right? Occult a star, and I wonder how long. I wonder how long that occultation lasted. It doesn't say. Um, June and July 2017 occulted 3 background stars. Team. Um, so here's a reference. Let's see where that brings us. Let's see. The primary goal of this project is to provide mission support for the occultation observation. Will be very sensitive to the rings. Rings, huh? Didn't know about that. Yeah, they don't give an occultation time. Kind of interested in that. Anyway, they use this occultation data to give them a little bit more information, right, about this this object. Um, as you can see in this slide here. Now let's see. Okay, so they're sort of thinking that maybe it's a binary object because see these are the ground traces, right? So it sort of looks like, you know, maybe there's not a lot of data here, but that's pretty convincing. Pretty convincing. So we'll have to see. We'll have to see. Could be interesting. Could be pretty interesting. Don't know what's going to happen there at all. But the interesting thing is that more and more of these objects are being um, discovered all the time. And so what I'm going to do is I'm going to go over here. This is the if you don't know about this site, the Minor Planet Center, you'll love it. If you like just to look at lots of numbers, then this is your site. Let me uh, let me just show you uh, a small example. So I forget exactly. Um, this isn't what I was looking for. I'm probably not going to be able to find what I'm looking for here. I'm not as prepared as I probably should be. I thought it was numbered objects. Oh, I don't know. Anyway, I don't even know what this is showing. Yeah, well, our instro, we're gonna find out, and whatever it is, it's gonna be fabulous. It's gonna be absolutely fabulous. And you know what New Horizons does after anybody's guess. But as I said, they've got power for 50 years worth of flight, and they're only what 12 years into it, uh, with lots of hibernation and stuff. So it's like, oh man, who knows where they're going to be able to go next. Anyway, if you like numbers and tables and all of that, this is your place. But where we're going to go is we're going to go to the minor planet list, and we're going to look at the list of trans-Neptunian objects. So they've separated these out, and and there are different families of objects, and so that's what they've done here. So we'll just look at the trans-Neptunian ones, and I don't remember how many there are. I don't think that there's really a way to. Let's see if this ASCII format. Let's see what that. Oh, that pretty much does the same thing. So yeah, not. I'm not going to be able to count these. Um, Wikipedia says something like 800 and some discovered so far, and you can sort of see the uh, the names here, right? So a few have were discovered back in 2017, but so far this year apparently we haven't found any, and part of the reason for that, and in fact, let's go to the Wikipedia page. Um, let's go Trans-Neptunian Trans-Neptunian object. So by definition, a trans-Neptunian object is any minor planet um, that orbits the sun at a greater average distance than Neptune, 30 astronomical units. So where's that list? Here's the list. So here's the list. Oh, did they say how many there were? So the first, of course, was Pluto. Took until 1992 to detect Albion. Um, okay, so as of February 2017, there were over 2,300 um, listed. So that's this list. That's this list. So apparently there's over 2,300 now. So that's pretty cool. Some of them are numbered and named appropriately. And of course, here is where's Pluto? There's Pluto right there. So that's very cool. But yeah, so here's all the trans-Neptunian objects, and these are just um, orbital elements. Oh, come on, let's. Here we go. So yeah, these are just the elements that you need in order to compute an orbit. Once you have an orbit, then you can generate um, what's called an ephemeris, and that's just a list of positions in the sky versus time. So it's just how these objects are moving, where they are in the sky at a particular time is an ephemeris. Um, so yeah, these are just all the different parameters that go into creating an elliptical orbit, a three-dimensional elliptical orbit. So there's a lot of them. There's a lot of them, and they're very, very, very far out. This A here, this A, that is the, I believe that that is the, um, I think that's the major axis distance in astronomical units. So as you can see, these are, you know, 40 times the distance between the Earth and the Sun, 46, 36. So yeah, anything more than 30, of course, is going to go onto this list. I'm seeing a lot of 40s, right? Just sort of doing a quick scan, mid 40s. We could take this table if we were so inclined. Let's see, can we? We could take this table and actually plot that column. You want to do that? It just so happens that, see, this is going to cause GNU plot some grief, this space right here. But this is the number I'm after. This is the column I'm after. And every other column just has spaces in between them. So what I can do is I can grab all of that, and we're going to copy, and we're going to open up Notepad. We're going to totally nerd out here, so just hold on to your hats. It'll be fine. Oh, I don't know if that's going to work or not. Oh, it should be. It should be. I'm not quite sure. Oh, it changes. No. Let's see if I can find a. Oh, here's a text version. Let's see what that looks like. Maybe it's comma separated. Nope. Darn. Um, shoot. Well, we're not going to be able to do that. That's okay. Um, anyway, so apparently there's like 2,300 of them now. So that's pretty nice. Um, that's pretty nice. Yeah, these are just way, way, way out there. And so far, um, I think we're just finding the big ones, right? That's my guess. This table here, as I recall, has some estimated, and I'm calling these estimated sizes, right? Um, so Albion, which was the first one found after Pluto, apparently is 168 kilometers in size. And yeah, that might be like aphelion distance then, because I'm seeing a Q over here, which is larger. So, oh, no, I was right. So what's Q? That might be aphelion. Yeah, I think this is aphelion is Q, and A is the semi-major axis. Okay. Anyway, so they give some sizes here, and as you can see, you know these things are pretty big, right? 398 kilometers in size. That's pretty big. 339. So, oh wow. So here's one that's 701. 701 kilometers. Incredible. I don't remember how big Pluto is. Did we pass it already? I don't remember seeing it. Chaos, Varuna, Ixion. Ixion is such a cool name. Lempo. Well, anyway, I'm not seeing Pluto, but as you can see, most of these are pretty big, right? Pretty big, 100 kilometers. Here's Sedna, 995 kilometers, almost 1,000 kilometers across. Orcus is really, really close to that too. Okay, so the video that you're seeing, the occultation occurred for zero point 0.2 seconds. Hmm. Okay. That's an interesting piece of information. So, okay. Let's see. So, yeah, pretty big, pretty big. I'm seeing, lots of large numbers. There's Pluto, 2377. You were pretty close there, Arenstro. So, pretty big, right? All of these. Goes on and on and on here. This is just the Wikipedia list, which I don't think is probably isn't complete, right? Probably isn't. Um, yeah. So, um, but of course, the ones here, this is a complete list. It just isn't. It doesn't give sizes. So what's this? Okay, ops. So remember the other day, I'm going to flip back to my ugly mug for just a little while. So you remember the other day, I was talking about this project that I thought was going to work to detect asteroids, unseen asteroids, using occultations, but and everything looked really really good. Everything looked really positive. Um, it sort of looked like it's like okay, a reasonable number of occultations are actually going to take place. Um, you know, it seemed really, really great. And then I got to the last thing, and that was to actually um, determine the probability that at a particular location that occultation will be seen. And what I based this on was some data I collected from that piece of software I mentioned, Occult 4. Occult 4, it will predict occultations for you. Cheers. One of the other things that it can do is it can tell you whether an asteroid is going to pass within a certain radius of a star, a certain distance of a star. And so what I did is I said, okay, tell me, for a set of asteroids, right? Tell me when that asteroid is 5 milli arc seconds away from a star or closer. So 5/1000th of an arc second. Now that's a very, very, very small angle, right? Very, very small angle, incredibly small. Uh, yeah, so there, you know, 1 degree of the sky is that length is about 2 full moons, right? I mean, if you were to line up 2 full moons, that distance is about 1 degree, right? Now there are 60 arc minutes in 1 degree, and there are 60 arc seconds in 1 arc minute. So in 1 degree, there are 3,600 arc seconds. And of course, there are 1,000 milliarc seconds inside of 1 arc second. So I'm talking about very, very, very small angles. So I told the program, to tell me when an asteroid passed within 5 milliarc seconds of a star. And that was sort of a arbitrarily chosen number. Don't know if I would change that now. I mean, I probably could, but yeah, that sort of seemed like a reasonable distance. But the showstopper there is that at the distances that we're talking about, in terms of trying to detect new and small asteroids, 5 milliarc seconds, that angle over a relatively long distance, say like 2.5 astronomical units, which is sort of the average distance between us and the asteroid belt. We're about 2.5 astronomical units away or so. Well, 5 milliarc seconds over 2.5 AU works out to be about 9 kilometers or so. So now you got to use your imagination a little bit here. You've got an asteroid out there that is going to move next to and potentially in front of a star. Okay, so what's happening, right, is that starlight is shining on the asteroid, and the asteroid, the actual shadow um, of the asteroid is moving, right? Because the asteroid moves, and so it's casting a shadow. And it just so happens that once in a while, that shadow, the path of that shadow, can intersect you. So um, that's what an occultation is just we fall underneath the shadow of that object. So if that object is 100 meters across, then the shadow is going to be that size as well, right? I mean, it's not going to change size. There's no reason to do that, right? There's no optics between us us and the asteroid. Um, they so it's just a nice straight um, shadow. Now there's a little bit of diffraction um, on the edges, but we can sort of ignore that, I think, for the most part. So yeah, a an object that is 100 meters across is going to cast a shadow that is 100 meters across on the ground. Okay, well, if at 2.5 AU, um, a an angular distance of 5 milliarc seconds translates to a distance on the ground of 9 um, kilometers. That means that anywhere within that 9 um, kilometer radius, um, the occultation can actually take place, right? That shadow is going to move somewhere within 9 kilometers of your location, right? But if this object is only 100 meters in size, that's, I mean, uh, the probability that it's actually going to pass over you is very, very small, right? It's 100 meters divided by 9,000 meters. So let's see what that is. 100. Grab the working calculator. It's still working. So go 100 meters. Got to put this down. Divided by 9,000 meters. That's 9 kilometers. So that's a 1.1% chance, right? That's a 1.1% chance that you're going to actually see this occultation of this very small asteroid. Um, so, that percentage changes as the object gets larger, right? Um, uh, because the size of the shadow is larger, right? If if you had a 9 kilometer asteroid at 2.5 AU, okay, then um, you've got 100% chance of seeing it, right? Because, or at least a portion of it. So, that's kind of interesting thing too, is that with that kind of resolution, um, uh, you know, the the um, the maximum diameter um, of the shadow may not pass over you, but just one side of the asteroid. So um, your occultation length is actually going to be shorter, right? Um, yeah, it gets into some complicated things that you have to try to think about. Anyway, that was the showstopper for this project that I had, that I thought it's like, what uh, it seemed like an easy way to detect very, very small and therefore invisible um, asteroids, especially the near Earth type that are potentially hazardous, right? But the problem is that with a 1% chance of actually seeing the occultation, okay, and I worked it out. Um, I showed you the paper the other day. think I've got it over. I think I've got it over here. Let me pull up because I want to show you yeah, I want to show you something that I discovered this afternoon when I was actually going through this because I want to finish this. I want to finish this paper, um, turn it into something publishable, um, uh, because even though it turns out that um, what I'm proposing isn't going to work. It's still, those kinds of things still need to be worked out because somebody else might have this idea and um, think like I did. And it's like, yeah, that should work. That should work. But when you run through all the numbers, it's like it doesn't. It doesn't work all that well, especially that last point with actually being able to observe the occultation. Um, so um, so not taking into account that last probability, okay, what I worked out was that if there are, let's just say, if there are a billion asteroids that are 100 meters and larger. Okay, if there are a billion of them, which there are estimates that go from 10 million to 10 billion. Right, it's a very, very wide range. Now, right now, the Minor Planet Center says, and I can go back to their main page. I'm not going to show you this, but as of right now, as of this very moment, okay, there are 779,736 known asteroids. Okay, now they estimate that there could be upwards of 10 billion of them, 100 meters or larger. So, whether that's a valid number or not, who's to say? But at least in the work I'm doing, I did an estimate um, at 10 million, at 100 million, at a billion, and at 10 billion. So at 100 million, oh, I'm sorry, at 10 million asteroids, if they were evenly distributed over the entire sky, and if all the stars down to 17th magnitude were also evenly distributed over the sky, then with 10 million asteroids, um, I would see 4 occultations per year per square degree that lasted longer than a tenth of a second. I would see 4 of them per year per square degree, tenth of a second or longer. Okay. Now, if there are 100 million asteroids, then it's just a factor of 10 more. So 43 occultations. If there are 1 billion asteroids, then about 437 um, occultations per year per square degree that are longer than a tenth of a second. And if there are 10 billion asteroids, then there are going to be 4,369 um, occultations per year per square degree. Now, all of that you have to multiply by the probability of actually seeing the occultation. So if it's 1%, if it's 1%, then nothing is worth it in terms of doing it unless you are sure that you have 10 billion asteroids, because then you would see about 43 occultations per year per square degree, with a 1% chance of actually seeing it. So, and 43 per year, that's, yeah, you'd be able to multiply that by your field of view of your um, detector, right? Your telescope and CCD, right? If you could see, 10 square degrees, then you would be getting up to what? 436 per year, which is still pretty sad, right? Uh, let's see, what is the Minor Planet Center says that so far this year, 3,760 minor planets have been discovered. So that's about 600 a month, right? Um, so if this system can't beat that, then there's probably no point. And that's assuming 10 billion asteroids. So, which I think is a stretch. I think that's a stretch. I think there are, but not 100 meters or larger. I think there are definitely 10 billion that are 1 meter or larger. Um, but that's a different calculation. So the bottom line there is like, okay, because the probability of seeing an occultation is so low, um, that's a showstopper. So I was going through all of this afternoon. Cheers. I'm going to get back onto the chat because I know that there's just a hustle over there. So I was looking at this paper because I want to finalize it, right? I mean, I said that I want to finish it, make it at least into a publishable form, and then see if I can get it published somewhere. If nothing else, right? I mean, I'll just self-publish, but get it out there. A little bit. It's not I mean, it's not one of these mind-blowing, incredible things. It's just a paper that could be referenced. So people don't have to go through the same painful exercise I did for several months. It was like an obsession. I had to figure it out. Uh, um, so yeah, what I realized, and our intro in the chat has sort of mentioned this already. What I realized is that um, is that there actually is a set of objects that this might work for. The two problems that 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 make detecting near-Earth asteroids and small asteroids. The two problems is that the length of the occultation um, can be really, really short, and so you're not going to be able to detect it, right? You're not going to be able to see it if it just blinks in like a 30th of a second, or less. You're just not going to see it. Uh, and this this shadow size, right? Um, and you would think that would be sort of greatly exaggerated at the distances of these trans-Neptunian objects. But it turns out, and I need to look at this a little more closely, but let me show you this plot that I made. I showed you a similar plot the other day, so I'll go through this again. And I know that we're running a little long, so hang with me. So what I wanted to do was I wanted to go over here. Oh, come on. I wanted to go over here. Oh, and I put it on my thumb drive here, so we can go over there. And it's asteroids, and it's this one. Oh, I don't have to do that. I can just double click on it. So now there's now there's five plots. five There's five plots here. I'm going to zoom in as far as I can, and then we'll look at each one of these plots. So this upper plot, and it's kind of hard to see the y-axis here, but this axis is distance in astronomical units, and I want to say that this is about 30 right here. I think this is, yeah, I'm not quite sure. It's hard to read. Um, it's overlapped a little bit, but yeah, 30. I think this is about 30, right? So this axis, of course, is time, and again, this is a 10-year period, right? So this is January 1st, 2017, and this is January 1st, 2027. So this is a 10-year period, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Haha. So this is wiggling like this because of the motion of the Earth around the sun, right? So this object is way out there, right? Way out there. But the Earth is sometimes a little further away and sometimes a little closer and further away, a little closer. And then this longer one, you see how we're slowly getting closer and closer and closer. This longer one is caused by the motion of this object, right? And what I've done is for these plots, I've made this a 100-kilometer diameter object. So this is actually one of the small ones, right? Out of that list that we saw, 100 kilometers, pretty small, pretty small. So this next plot down is, I've changed this a little bit here. This is now logarithmic, right? So this goes from 1,000 up. Here's 2,000, 3,000, 4, 5, 6, 7, 8, 9, 10,000. So this goes from 1,000 to 10,000 micro arc seconds. This is the apparent diameter of this asteroid in micro arc seconds. So 1,000, 2,000, 3,000, 4,000. So it's around 4,500 4,500 micro arc seconds. So what, 4.5 milli-arc seconds in size? That's for 100 kilometer sized object. So, you know, because it's so far away from us, its apparent size really doesn't change all that much. Changes a little bit, but not all that much. So that's why that looks relatively flat. As you can see, it's biggest when we're closest. And this does have a gradual slope up, right? Because, I mean, it is slowly getting closer to us in this time period. So, yeah. So this next one, this next plot down, this is the apparent motion in micro arc seconds per second. So this is how it's moving in the sky over that same time period. So sometimes it moves a little slow, and sometimes it moves fast, and then slow, and then fast, and then slow. And again, this is a logarithmic scale. So this is 100. Here's 1,000. Here's 10,000. So it's going 100, 200, 300. So somewhere around 300 micro arc seconds per second, up to, oh, I don't know, a little over 1,000 micro arc seconds per second. So it's at these slow times where the possibilities of the occultations um, increase in terms of the length of time, and that's actually the next plot. This next plot is the number of seconds that it takes for the object to move one of its apparent diameters. So that this plot here is basically the length of the occultation that would take place. And as you can see, for this entire time period, we're talking about multiple seconds of occultation time. Multiple seconds. So that's very, very cool, right? I mean, we don't have to worry about this, you know, tenth of a second stuff, right? We can relax and be like, okay, this thing is gonna, you know, at certain times, right? This thing is moving such that if there was a star behind it, it would have an occultation time greater than 10 seconds. So that's pretty good. And this is the new plot. This is showing the probability of actually seeing an occultation, right? And as I said, it's based on this 5 milliarc second distance being translated down to the ground. Now, at 30 AU, we're talking about a much larger distance, right, on the ground. But that's sort of compensated for because of the size of the object. Remember, it's a 100 kilometer diameter object. So the cool thing is that this number here on the side, I don't know if you can see it all that well or not, but this is a percentage, and it goes from 43 up to 51. So there is going to be a time in the next 10 years, right, where there's greater than a 50% chance that you're going to be able to see an occultation occur if there's a star in the right time at the right place, right? And it's going to be, well, several seconds, right? So as long as this probability is pretty high, right? I'd like it to be around 50% or more. As long as that's the case, then all those numbers I quoted to you before are valid, right? So if there are, and I mean, I'm going to have to go back and calculate these numbers because, these are based on saying, okay, if it's a tenth of a second or more, um, well, all of these are, right? These are several second occultations. So yeah, I'm not quite sure where the numbers are going to lie, but even if there are um, only 100 million of these, okay, so right as of now there are like 2,300. So we're just guessing that there are more. Um, but even if there are like 100 million more, then I'm thinking, and this is where I sort of have to end. I'm going to stop sharing because we are going a little bit long, but I'm going to have to run through these calculations. But I'm thinking that based on the fact that the occultations are going to be pretty long, and that because the size of these objects is so large, the probability of actually seeing an occultation is good, right? If I can get 50% chance or better, then that's a really 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 good chance. Um, you know that means half the occultations that I observe, I will actually see something, and that's absolutely fantastic, right? So I've got to take that calculation into account here. I need to change the the duration. So luckily, I've got this all laid out in a spreadsheet. So spreadsheets are probably one of the greatest things uh, ever made. Does somebody want to agree with that? Yeah, um, Arinstro, I'm not sure. Um, I I don't know how they collected their data. I'm not exactly sure if they took multiple images of the same thing. You know what? You know what? They I th- well, what you could do, what you could do is, and I think this is probably how they measured proper motion, is that um, because they didn't have proper motion in data release one, right? Because it's like, how do you measure that? But data release two, you've got two sets of data now. So I'm thinking that you can probably blink data release one and data release two if you can get the actual images, which I think are available. I think the actual images they took, I think those are available. Um, uh, but yeah, yeah, spreadsheets. I think they're absolutely great. So yeah, I've got this all laid out um, in a spreadsheet. I'm going to have to change things, but this exercise has sort of breathed new life into this project, as if I, you know, need something else to do. But it sort of changes the focus though too, because the focus, the initial intention was to do this to detect small sort of near Earth asteroids, And now it's going to be like completely the opposite, right? We're going to look for uh, well, as small as we can. I'm going to have to work that out, but um, uh, trans-Neptunian objects. And I'm thinking that, as I said, because they're big and because they move slowly anyway, so the occultation times are going to be pretty long. Now, you mentioned 2/10 of a second. That's pretty fast for a trans-Neptunian object, I think. I think. Going to have to look into that a little bit. Um, So, but yeah, it's possible that it was um, that short of a time period because they caught it, um, uh, not like occulting right down the center, but off to one side. So yeah, don't know. But anyway, so yeah, it sort of breathed new life into this project, changing the focus a little bit. I think this is sort of um, um, what's um, at least in the business world called a pivot. So yeah, I think a pivot is going to take place, and yeah, now I'm going to have to work all this out. So, but yeah, it shouldn't be too bad because I've got, as I said, I've got the spreadsheet. I think that's all I'm going to need. So yeah. So stay tuned. That's an interesting project that I thought was dead, but I think it might have some new life. So all right, I'm running really late. I'm really glad that you all came in. I'm going to get out of here for now. Um, Thanks for joining the circle. This is, just a lot of fun, right? We're just having um, a lot of fun talking astronomy for, I try to keep it to an hour, but I don't think it really ever is, because there's always, that's the thing about astronomy is that there is so much. There's so much that you can just go on and on and on. And I definitely can. So if you want to be part of the panel, send me an email, cosmiclettuce@gmail.com. And when I start up the Hangout, I will send you a link, and you can be a part of the panel. I know Bobby's enjoying that. I want to engage him a little bit more. Um, don't I don't mean to sort of um, keep him um, out of the conversation. I just have to practice that a little bit and be a little bit more mindful. So yeah, all right. I'm gonna get out of here for now. Um, Trans-Neptunian objects. I I think that there are a lot of them. I really do. I think that there are probably as many of those as there are estimated to be um, asteroids inside the solar system or inside the orbit of Neptune. Um, and if that's the case, then this occultation thing might have some life. It might just have some life. We'll see. We'll see. All right, I'm gonna get out of here for now. Subscribe if you haven't. Hit the thumbs up or the thumbs down if you haven't. And I'm going to get out of here for now. I will see you on the spin 22 and a half hours from now. All right. Take care, everybody. Bye.